Hello, Physics 30s. In today's lesson, we are going to begin a new unit of study, and the name of that unit of study being Modern Physics. And by modern physics, I mean it was modern physics over 100 years ago, but for whatever reason, we're still going to refer to the information that we learn about today and moving on as modern. And in this lesson, we're going to describe electromagnetic radiation, an electromagnetic wave, look at Maxwell's principle of electromagnetic radiation, an experiment that was performed to support the principle, and then briefly just describe the different parts of the electromagnetic spectrum. Learning outcomes are to 1, describe qualitatively how all accelerating charges produce EMR. 2, compare and contrast the constituents of the electromagnetic spectrum on the basis of frequency and wavelength. And 3, explain the propagation of EMR in terms of perpendicular electric and magnetic fields that are varying with time and traveling away from their source at the speed of light. That acronym EMR is an abbreviation for electromagnetic radiation. Before we kind of jump into the new material, we're just going to take a moment to review some of the important principles that related electricity to magnetism and vice versa. So this was information that we discussed back in the magnetic forces and fields unit of study. One of the scientists we talked about back then was Hans Ørsted, and he stated that an electrical current in a conducting wire produces a magnetic field perpendicular to the current. Just as a reminder, this is the experiment where he rented a lecture hall and invited 50,000 people to come and observe him proving that electricity and magnetism have no connection. Again, the idea was you took a wire and then put a compass in front of the wire, compass needle pointing upward, and then he ran an electrical current through the wire, and then it caused the compass to deflect in a direction that is perpendicular to the direction of current, which tells you there's a magnetic field that's perpendicular to it. And we can use the first-hand rule to predict that. If you took your right hand for current and pointed it towards the top of the page, then the curl of your fingers from a top view perspective would be in a counterclockwise direction. The important thing about Ørsted's observation was that he showed that electricity can lead to magnetism. We also talked about Michael Faraday. Michael Faraday's law stated that a changing magnetic flux will induce current in a conductor. So let's give an example of one of these scenarios. So let's say that we have a broken wire. And this broken wire is over top of a magnetic field. And most of the magnetic field is directed into the page. Use a variable b to represent the magnetic field. And then we can take a conducting object. So we can take like a copper rod or something, and then we can put it over top of the circuit. So it kind of completes a circuit for us. And then if we take this rod and if we move it at a certain velocity towards the right, what's going to happen is the magnetic flux that's enclosed by the area of the completed circuit. So the enclosed area of the completed circuit would be this area that's shaded in. And as you pull that rod towards the right, you're going to change the number of magnetic field lines that are enclosed in that area. If you change the magnetic field lines enclosed in an area, you change the magnetic flux. And as long as you have a changing magnetic flux, you can induce a current. The important consequence about this one is Faraday's law tells you that you can start with a magnetic field. So you can start with magnetism. And by moving that rod, you can actually induce currents. You can get like electricity out of it. And this goes with that concept of symmetry in nature. So the symmetry in nature is, can you go from electricity to magnetism? And if you go from electricity to magnetism, can you go in the reverse direction? And yes, you can go from magnetism, specifically a changing magnetic flux, to getting an electrical current or electricity. So those are our two fundamental principles of electromagnetism so far. Along comes another, I believe he was a mathematician, not a scientist, James Clerk Maxwell. This is all the way back in 1855. Basically what he did is kind of like the same experiment that Faraday did. So we'll go back to that picture in just a moment. And he confirmed that a changing magnetic flux will induce current in any object. So not just in conducting objects. It will also induce it very briefly inside of an insulator. Okay, so let's go back to this illustration. So the assumption we've made so far is that Faraday's law tells you a changing flux can induce current in a conductor, and we can use the modified third-hand rule to predict what the direction of current would be. So the way I would do it is take your right hand, because we're talking about current. Your thumb points in the direction that you're moving the object. Your fingers point in the direction of the magnetic field, which is into the page, and your open palm would face towards the top of the page, which would tell you that in this situation, you have an induced current that is going to go up, and then it's going to go towards the left, then down, and then towards the right. And then from our perspective right here, that would give us a counterclockwise current. I think that's counterclockwise. Yes. Okay. What James Clerk Maxwell's experiment showed was that you don't need a conducting object. You can actually induce current in an insulating object. Very briefly, though. I mean, there's so much material resistance in an insulating object that you could induce current maybe for like just like a quick instant and then it's gone. But nonetheless, we can still make that observation that a changing magnetic flux can induce current in any kind of an object. Here's where it kind of takes a bit of a leap of faith, I suppose, in taking this observation and expanding it heavily out to another idea. So he believed that not only can you induce current in any object, you should actually be able to perhaps induce an electric field in empty space. You don't actually even need an object to do this induction in. Again, that seems like a drastic jump in terms of going from like point A to point B, but that's where we're going to go with. I suppose the way to think about this is, in order to induce current, you need an electric field. Electric field is a region of influence that can affect electrical charges, including stationary electrical charges. So his idea is basically that a changing magnetic flux or a changing magnetic field can actually produce a changing electric field, and that can induce current. However, his idea is that we don't need a conductor or an insulator to do that in. We can actually create an electric field in empty space. Maxwell's principle states that a changing electric field in space will create a changing magnetic field. And if you continue on, a changing magnetic field will create a changing electric field. And if you have a changing electric field, it creates a changing magnetic field. I suppose I could call this self-propagating, in that a changing electric field produces a changing magnetic field, which in turn produces a changing electric field, changing magnetic field, etc. It's the interaction between these fields that propagates something called an electromagnetic wave through space. Let's look at an illustration of what an electromagnetic wave would look like and try to clarify this principle. This picture looks really complicated initially because there are things going on in all three planes of motion. So on the right side of the picture, I've just shown my three-dimensional Cartesian grid to kind of help out with what's going on here. What I'm going to focus on is, first of all, the changing electric field. Actually, you know what? Let's do the changing magnetic field first, because changing magnetic field we can associate with a changing magnetic flux. Okay, I'm just going to do this with a different ink color. Okay, so let's say we have a changing magnetic flux, which could be represented by a changing electric field. So I have a changing magnetic field or changing magnetic flux. So that's B. This would line up, if you look on the graph here, with the z-axis, I believe. Yeah, because it'd be coming kind of like into and out of the page. So that's where you'd have your changing magnetic field. These lines right here just show that the magnitude of the magnetic field is changing. Okay, so let's say we do something where we have a changing magnetic field or a changing magnetic flux. Well, what happens if you have a changing magnetic field? A changing magnetic field will, according to Maxwell's principle, also produce a changing electric field. So we also have a changing electric field. This changing electric field is in a different plane of motion. This one would be in the y direction. So this is where E would be. So your changing magnetic field, the green, produces a changing electric field. So that's E. Then what does a changing electric field do? Well, a changing electric field would produce a changing magnetic field. So here's my changing magnetic field. Let's draw a few of these lines. And what does a changing magnetic field do? It produces a changing electric field. So like I said, the production of an electromagnetic wave is self-propagating. So from some kind of source. So some kind of source would just be the source where you have like a changing magnetic flux or a changing electric field. From this source, this electromagnetic wave would self-propagate. And the other thing we have is we have the direction that the wave would travel. And the direction the wave would travel is also perpendicular to both the direction that the electric field and the magnetic field is oscillating. So the direction the wave moves would be in this direction away from the source. So that would be in the direction of the x-axis. So the direction of the wave propagation. When I say wave propagation, it just means the direction the wave energy is being transferred. Direction of propagation. Okay, now let's summarize some points about this, because I realized it was a little bit confusing. But the way we draw an electromagnetic wave is we have three things that are perpendicular to each other. We have a changing perpendicular magnetic field. So that's the one that's in the z-axis. We have a changing electric field, which is perpendicular to the magnetic one. That's in the y-axis. And we also have perpendicular to both of those, the direction the wave is going to move outwards from a source. And that self-propagation between the changing electric and magnetic fields is what we refer to as an electromagnetic wave. How do you produce an electromagnetic wave? An electromagnetic wave can be produced by an accelerating electrical charge. So let me give an example of this. One of the easiest examples to explain how you can produce get an accelerating charge to produce an electromagnetic wave is to look at AC current. AC current means alternating current. Normally in an electrical circuit, if it was a DC circuit, you would just have an electron and it would just simply go in one direction, or just follows like a defined path. For alternating current, you'd have a bunch of electrons that are kind of like side by side. But all they do is they just vibrate in place just ever so slightly. So they might just like oscillate back and forth, can just go like vibrate left, right, left, right, left, right. And they do it at a certain frequency. They are definitely accelerating because let's just take one of these right here. So let's take an electron. And we'll say it's just slightly oscillating or vibrating back and forth, back and forth, back and forth. It's definitely accelerating because you're having constant direction changes from going towards the left and then back towards the right. And the only way that could happen is if your velocity is actually changing. So that's one way you can get an accelerating charge, just alternating current. But we're going to talk about a lot more ways that we can deal with accelerating charges to produce an electromagnetic wave later on. 2. The frequency of oscillation of the charge is equal to the frequency of the electromagnetic wave that is produced. Okay, so let's go back to this previous picture. Let's kind of just get rid of a bunch of this junk here. So let's say that the source of this electromagnetic wave is an oscillating electron. So kind of think of it like this. Here's my electron, and it's just oscillating up and down, up and down, up and down. The direction that I see the blue electric field would just match the direction of the oscillating electrical charge. So when the electron is going down, I'd see the wave like dipping down. When the electron is going up, I would see the wave dipping up, or not dipping up, I'd see the wave going up then. If this electron oscillates with a frequency of, let's say, 60 hertz, so 60 hertz would mean 60 complete oscillations in 1 second, the frequency of the electromagnetic wave is going to match it. You have to remember, this electromagnetic wave, this is a stationary static picture, but an electromagnetic wave would constantly be oscillating. So you'd have, like, for example, like this crest would oscillate down to a trough, and then it would come all the way back up to the crest. That would represent one period. And whatever the frequency that the accelerating charge oscillates at, that is also going to be the frequency of the electromagnetic wave. And if you want to think of the frequency of the electromagnetic wave, it'd be like the number of times that you have the wave go from its crest to its trough and back in 1 second. So these two numbers would just match. 3. The oscillating fields are perpendicular to each other and to the direction of wave propagation. Well, once again, we've already talked about that. When we looked at this picture, we identified that the electric field is oscillating in the Y direction. The magnetic field is oscillating in the Z direction, and the direction of wave propagation is in the X direction. All three of these axes are perpendicular to each other. 4. All electromagnetic waves travel at the speed of light in a vacuum. So that's 3.00 times 10 to the 8 meters per second. And they obey the equation V equals F times lambda. V equals F times lambda is the universal wave equation. Okay, the universal wave equation can apply to any kind of wave. So that includes both mechanical waves, which we talked about back in Physics 20, and an electromagnetic wave, which is what we're talking about right now. And it turns out, without even knowing it, we've already been dealing with how electromagnetic waves behave, because we dealt with that in the last unit of study. In the last unit of study, we talked about light and optics. So now we're starting to describe in more detail the wave nature of light, and all electromagnetic waves can do the things that we dealt with in this previous unit on light and optics. So that means that if an electromagnetic wave hits, like, for example, a mirror, it can hit it and it can reflect in accordance with the law of reflection. If an electromagnetic wave goes from one medium to another, there's a speed change, which means it can refract. If an electromagnetic wave goes through some tiny slits or around sharp objects, it can spread out or diffract. And if electromagnetic waves overlap, they can interfere. Interfere, we get that interference pattern of alternating antinodes and nodes. And the other thing they can do is electromagnetic waves can be polarized. Polarized means if you do polarize something, you can just reduce the number of planes that it can actually vibrate in. We're going to see a bit of a connection as we go through this unit of study, where one scientist will come up with a really good idea or a really good experiment, but they need some support in actually confirming their initial idea. We saw this a little bit with Thomas Young's experiment. So Young did the double slit experiment. It does clearly show that there is a wave nature to light, but a lot of people didn't believe it. Isaac Newton believed the particle nature of light, and it took some other scientists, which I can't remember their names. I think it was like Fresnel and Poisson, to do some experiments and some mathematical modeling to support it. So just like with James Clerk Maxwell's idea that dealing with electromagnetic waves, we need someone who can actually support that the existence of an electromagnetic wave and how exactly it behaves. Okay, so we have Heinrich Hertz's experiment. And the point of this experiment is its support for Maxwell's prediction, dealing with the fact that a changing electric field can produce a changing magnetic field and vice versa, and they're perpendicular to each other. Well, let's look at the setup of this experiment. Pretty simple setup. So what I have on the left-hand side is I have a high voltage source, and this is connected to a circuit that has a very small gap. Now, normally, if you have a gap, the circuit's broken and you can't have any motion of the electrical charges. However, if we have an electron here, and if the voltage source is high enough, we can get the electron to actually jump across this gap. When it jumps across this gap, we observe it as a spark. But we can only do this if our voltage source is really, really powerful. So we have a powerful voltage source that is capable of taking an electron and making it jump across this gap. Somewhere across the room, we have another circuit, and it's broken, but this one has no power source. So at first glance here, it doesn't seem like there is anything that would be capable of actually causing an electron in this one to jump across the gap. If you don't have any battery source, how could you possibly make it jump across the gap? What he observed is that if you have an oscillating spark across one gap, it will induce a spark across the second one, which means that if you have an electron and it starts to hop across this gap and it comes back across this one, then I'm also going to see a spark that oscillates across this gap as well. Okay, let's try to explain why this is the case, and then I'll go through all the summary notes afterwards. So first things first, let's identify what is the source of an electromagnetic wave. Okay, your source of all electromagnetic waves, and this is really important, this is a key concept, is the source of an electromagnetic wave is an accelerating charge. So let's say this voltage source is an AC voltage source. So what an AC voltage source is it could take an electron and it's just going to have it oscillate back and forth across this gap at a certain frequency. Now, let's just worry about an electron here and then jumping to this side. Now, when it jumps to this side, if you have an electron that's moving from one side to another, that is going to be the source of an electric field. Remember, electric fields are produced by charges. So let's try to draw the electromagnetic wave here. So as this guy jumps across, we would see an electromagnetic wave that gets produced like this. Okay, that's my electric field, and it's changing depending on whether the electron is jumping up across the gap or down across the gap, and we're going to call this E. I'm going to create a three-dimensional grid. Yeah, let's do it like this. So we'll say this is Y, we'll say this is X, and we'll say this is Z. And let's follow how this electromagnetic wave works. Okay, so when this accelerating charge that's bouncing up and down across the gap, when it moves, the electric field is going to follow along with it. So we have a changing electric field. So let's draw a little bit of that electromagnetic wave. And what does this changing electric field do? Well, according to Maxwell's principle, a changing electric field would produce a changing magnetic field. Specifically, a changing magnetic field that's perpendicular to the changing electric field. So I'm going to draw the perpendicular changing magnetic field in the Z direction. This is going to be really hard to do, okay? So I'm trying to draw it so it's following this direction here. So my changing magnetic field might look something like this. Okay, well, it looks like it roughly follows that direction I've got there. I'm just going to draw a few of the arrows. There's no need to do tons of them. Okay, so I have a changing electric field produces a changing magnetic field. And according to Maxwell's principle, what does a changing magnetic field do? Well, a changing magnetic field in return produces a changing electric field. So now we're going to continue the electric field on. So this electric field would go down here. So that's E. And again, E is going to be in the direction of the y-axis. And what does a changing electric field do? Well, a changing electric field produces a changing magnetic field. Perpendicular, of course. And what does a changing magnetic field do? A changing magnetic field produces a changing electric field. Okay, and we'll stop there. This is as far as we need to go to explain what's going to happen. Okay, so got my changing electric field. Now, if you had an electron here, a stationary electron, which is what happens. If the circuit's broken, then none of the electrons would be moving. The only thing that could get this electron to move would be a changing electric field. Electric fields are capable of influencing any kind of electrical charge, whether they're at rest or moving. A magnetic field can only affect moving charges. So what would this do? Well, as this changing electric field passes through this region, it would then cause this electron to start jumping across the gap because the electric field is directly in line with this gap. So it would influence a stationary charge so that when the electric field is directed downward, it hops down. Then later when the crest turns back into the trough turns back into a crest, it would then hop across here. So what we'd see is we'd have if I can induce a spark across, if I have a spark jumping across one gap, I can induce a spark jumping across the other. And this does support the idea of there being an electromagnetic wave that is produced by this accelerating charge from the AC current. Now look at some observations. If you take the gap and you rotate it by 90 degrees, you will not produce a spark. Okay, so here's what I mean by this. You realize the picture is starting to get like really, really complicated. So let's get rid of some of this junk here. Okay, so let's say that here, I'm just going to draw the electric field in a reverse direction. So say the electric field is directed upward. And I'm just going to draw the perpendicular magnetic field. And we'll also draw that stationary electron. So in this situation, because the stationary electron's here, the electric field will cause it to jump across the gap towards the top. Now, if you take this wire and you rotate it by 90 degrees, so rotating it by 90 degrees would mean, if we look at my axes, so you have Y, X, and then Z. So right now, the magnetic field's in the Z direction, the electric field is in the Y direction. So if you were to take this wire and then rotate it, so I'll try my best to show it now, it's going to be lined up with the Z direction. So I took this wire and I rotated it. It might look something like this now. So let's draw the gap. So we flip it by 90 degrees. So now what we have is the gap is lined up with the Z direction, the magnetic field. What you notice now is that there is no spark. Okay, there is no spark when the electron here is in line with the magnetic field. The reason being is because, once again, this is a stationary electron and that circuit is broken. When the magnetic field lines up with this, the magnetic field cannot have any influence on this electron because the magnetic field can only affect moving charges. And since the magnetic field has no effect on the stationary electron, we no longer see the spark across the gap if we rotate this thing by 90 degrees. So this actually does confirm that we have an electromagnetic wave because it's showing the perpendicular nature of the electric and the magnetic fields. One other observation, we're not going to talk about it right now, but the speed of the electromagnetic wave was also determined from this experiment. It involves something using a zinc reflector plate. And again, I'm not going to go into like the details of like how this was determined, but when they did this, they were able to identify the speed of an electromagnetic wave is in the range of 3 × 10⁸ meters per second. That's interesting because this electromagnetic wave in this experiment, we can't even see it. It's not visible light. It's some other kind of form of electromagnetic radiation, yet it still shares the same speed of light value from the light, that visible light we talked about in the previous unit of study. Conclusions? You only get a spark across the second gap when the electric field needs to be in line with the gap. When the electric field's in line with the gap, it can influence that stationary electron. And if it influences that stationary electron, it can cause it to hop across the gap, and that gives me that spark. And when the magnetic field is perpendicular to it. If the magnetic field is parallel to the gap, then it has no influence. So we want to set it up so the magnetic field is perpendicular to that gap. 3, it's also proof that an electromagnetic wave exists, because again, we have clear evidence of this perpendicular nature between the electric field and the magnetic field. And it also confirms that, well, if we prove that an electromagnetic wave exists and an electromagnetic wave travels at a speed of 3 times 10 to the 8 meters per second, that tells me that visible light is an electromagnetic wave. Let's try to summarize all of the different points we talked about today, or at least a few of them. So first one, what exactly is an electromagnetic wave? Well, all waves are energy carriers. They're just energy carriers from one spot to another. In terms of a mechanical wave, it is energy that's transmitted due to collisions between particles that make up the medium. In the case of an electromagnetic wave, well, it's not particles that are like moving, it's just the magnetic fields that are moving. They're changing direction constantly. Point 2, from a source, electromagnetic waves will travel in every single direction from that source. And again, we talked about that in the last unit when describing sources of light and the wave rays, we'd actually draw in every direction coming from that source. 3, this is a huge difference between an electromagnetic wave and a mechanical wave. Mechanical waves require a medium to travel through because mechanical waves are generated through collisions between particles. So you need to have particles in a medium. Electromagnetic waves do not require a medium to travel through because an electromagnetic wave is just made up of oscillating electric and magnetic fields. That doesn't need a medium for it to actually exist. And 4, all electromagnetic waves are produced by accelerating charges. We'll talk about various ways that we can have accelerating charges that can produce EMR. One other thing, just to wrap the lesson up, we'll talk about the electromagnetic spectrum. So I'm sure you've had some exposure to this before. So our electromagnetic spectrum is made up of, we have radio waves, we have microwaves, we have infrared radiation, we have visible light. That's what we talked about completely in the last unit of study. We are restricted just to visible light. We have ultraviolet rays, we have X-rays, and we have gamma rays. With the exception of visible light, we cannot actually see directly any of these forms of electromagnetic radiation. There are some cameras that can actually give you a picture of what infrared radiation looks like. And I think like bumblebees actually have something in their eyes that can also see ultraviolet radiation. But of all these different types of electromagnetic waves, we can only actually see, humans, visible light. What I want to show you on this electromagnetic spectrum is just the connection between the frequency and also the wavelength of the different parts of the spectrum. So if we look at increasing frequency, radio waves have the lowest frequency. Then we go to microwaves, infrared radiation, visible light, ultraviolet, X-rays, and gamma rays. Typically, the way I try to memorize the magnitude of the frequency of these waves is I use the visible light as kind of like a reference point. So visible light as a reference point would have an exponent of 10 to the 14 hertz. To get to the next part of the spectrum, you just look at increasing or decreasing the exponent on the 10 by 2. So for example, if we went from visible light to ultraviolet radiation has a frequency somewhere around 10 to the 16 hertz. So we increase the exponent by 2. X-rays, we'd add another 2. It'd be around the magnitude of 10 to the 18 hertz. Gamma rays, 10 to the 20 hertz. Infrared, so now we start subtracting by 2. So this would be like 10 to the 12. And I think radio waves and microwaves, we're starting to get into like 10 to the 10 hertz. And then somewhere like maybe perhaps like 10 to the 8 hertz. But they have quite a bit of range too. But it's just kind of like a a simple rule of thumb in terms of memorizing the approximate magnitude on these different parts of the electromagnetic spectrum. The other thing to notice is that as you go from radio to gamma rays, even though as a frequency increases, the wavelength actually drops. Well, we can confirm that really easily. Our universal wave equation tells us that V is equal to F times lambda. So if we calculated lambda, it'd be equal to V over F. If V is constant, so let's say we had all these types of electromagnetic radiation in the same medium, that would tell me there's an inverse relationship between the wavelength and the frequency, which means that when the frequency is big, like it is for a gamma ray, the wavelength is smaller. And when the frequency is small, like it is for a radio wave, the wavelength would be large. The only other thing of note on this spectrum is it's just important to have a general sense of what the wavelength range is for visible light. And we've already talked about this in the last unit. So my range of visible light is approximately from 400 nanometers to 700 nanometers. 400 nanometers is violet light. And then 700 nanometers is approximately where you have red light, although it can extend beyond that range. So just kind of like an important wavelength range to identify whether we're dealing with visible light or not. Okay, that's it for this lesson. I realized it was super theory intensive, but hopefully now you have an idea of what an electromagnetic wave is based on James Clerk Maxwell's principle, which just tells you that an electromagnetic wave has perpendicular electric and magnetic fields that are also perpendicular to the direction that a wave moves. And you can reinforce your understanding of this material by completing the assignment called Electromagnetic Radiation. And then the next lesson, we're actually going to take a step back and revisit some early atomic models, which we're going to have to make some modifications to now that we know Maxwell's principle of EMR. And I'll talk to you then.